Hey, you're Evans, thanks for coming to the webinar today. So this is a really quick video. We're going to do diffusion in a few minutes. Going to go through all the GCSE examples. We've got diffusion in terms of dissolving and into solution. We've got over here, we've got diffusion in gases. Now this is the one that you guys are going to recognise the most. This is our ammonia and HCl. And then finally we're going to try and do a comparative of diffusion in gases, comparing nitrogen dioxide, which is brown, to bromine, which is also brown. So okay, first one's really quick. I'm going to get a NAM to see if we can zoom in on various bits at times. So the chemical I'm using here is a chemical called potassium permanganate. Now potassium permanganate is a lovely colour. It's very, very dark and it's a dark purple. See if I can get a little bit more out. So this is a dark purple solid and it almost, you're allowed to say it's black. Now potassium permanganate is not very nice. It is a powerful oxidising agent. But you'll recognise this because it starts off black. You try and pick it up without crushing. Let's just go big. Let's go big. There we go. And drop it in there. Okay, so if a NAM zooms in, what you can see happening here is that you have got the solid potassium permanganate sitting on the bottom. And you can see, as it's fallen in, you've got this rather beautiful purple colour. But as you can see down here, it is getting darker. Now what's happening is two processes. The first one is it's dissolving. So the water molecules are colliding with the particles in the potassium permanganate solid and it's pulling it apart. And that description you need for your GCSE. Dissolving, the collision of water molecules with the structure and those water molecules pulling apart that structure, forming smaller molecules which are invisible. Now you can see that it's very dark at the bottom. But what will now happen over the course of a few minutes is this purple, this dark purple colour, is going to slowly spread through it. Now this is quite a difficult practical demonstration to actually show, because the problem is when you drop it in, you get this pale pink throughout the colour because it dissolved as it dropped through. But if you look from kind of our height over here, you can see how dark it's now becoming at the bottom. Now we're going to come back to that at the end of the video, and what we're hoping to see is a beautiful dark layer at the bottom, followed by the paler on top as the diffusion process occurs. Okay, so that's diffusion in solutions. So solids dissolving, forming solutions. So then we're going to come to this one. Now this one is the most famous one, and I have a man sitting right across the way from me. So this is the most famous one. This is a diffusion tube for looking at gases. And we've got two gases we're looking at in this particular demonstration. The first gas is hydrogen chloride. Now I need to stress this, folks. Hydrogen chloride is HCl. What you see here is a bottle that contains a solution. This is hydrochloric acid, which is the solution, but the gas we're going to be observing is hydrogen chloride. Just to show you that that gas does exist. So what I'm going to do, if I take the lid off, and then now get a little bit closer, what you're able to see is, you can see that it's fuming. This is giving off a very small amount of HCl gas as a vapour. This is hydrogen chloride gas. Now this gas, we can test for it. We test for this using litmus paper. Now the litmus paper starts off blue. Now you realise it stays blue until we dampen it. If we now put the damp litmus nearby, then we see that the blue litmus turn red. So we're seeing that, it's because the reason being is the gas, it didn't work when it was dry. When it's dry, we see no colour change. But when it's damp, it turns red. This is because the gas itself is not acidic, but once it's reacted with water, it forms hydrochloric acid, and we then see it as our red on our litmus. If I do this on universal indicator paper, again, it needs to be damp. So I'll dampen, this is my universal, meant to be green of course. If I put the damp nearby, we see the universal litmus paper, universal indicator paper turn red. So there's our hydrogen chloride gas. I'll put the lid back on that one. Let's go over to this side. The second gas we're looking at in this tube is we're looking at ammonia gas. Now once again, this is ammonia in solution, otherwise known as ammonium hydroxide. And if I take the lid off, there is no gas apparent at all. This is because ammonia, when it leaves as a gas, doesn't react with the water molecules in the air, so you don't tend to see it, it's completely invisible. But that gas is there. Now ammonia is a base, pH 11, and if I've now got red litmus paper now. Once again, doesn't do much when nearby, but when I add it water, we should hopefully... Oh, have I picked up... That's blue, I think. Hang on a second. I've got 2 sets of blue litmus. That's amazing. We'll try with the universal. So I've got universal indicator paper. Oh look, isn't that interesting? Changing colour when it's nearby, even when it's not damp. But it's turning green. If I dampen it, we'll see it turn, in fact, our lovely dark purple colour. So that's, by the way, it's actually gone blue now. Anand can actually probably, can you smell the gas at this point now, Anand? Can't really miss the smell of ammonia. Yeah, strong smell. Both, by the way, alkali and acid, both hazard symbols will be corrosive. Get that one out of the way. Okay, so what we now need to do is we now need to look at what happens when these gases come in contact with each other. Now what we're going to do is just really quickly show you what happens. You see absolutely nothing at the moment, and then if I bring the HCl nearby, what we see is a white smoke. So the gases, there we go. So the gases, when the gases come into contact with each other, they form a white smoke, which is a solid ammonium chloride. Now what we're going to do is we're going to have the same thing. If I separate them, the ammonia goes completely quiet over on that side. We've still got some vapour coming off, but that's our normal HCl fumes that we saw before. If you notice again the smoke, we get a very white smoke of ammonium chloride when they're brought together. So what we now need to do is we now need to see if we can actually use these to look at the rate of diffusion. So what at this point I'm going to do is I'm just going to put some gloves on. These are both very, very corrosive. So the precautions here is, even though I'm wearing goggles, not a great precaution for liquids and solutions that you're handling, because if I spill this, this is going to get onto my skin and it'll burn me. It is very, very corrosive. So what I'm now going to do is, now that I've got some gloves on, I'm going to add, just going to grab my caps, which I think, where have I left my caps? Oh, over here. Okay, sorry about that. Okay, so I've got 2 caps. The first thing I'm going to do is I'm just going to put some HCl, a small amount of HCl here. You can see why I need gloves here. Yeah, a small amount of HCl onto the cotton wool. I'm trying to enter that into the tube here. Now I need to be fairly brisk with this because it needs to be fair. So if I put the lid on here, I now do exactly the same thing with the ammonia. Pour a small amount of the ammonia here onto that one there. And I put that one inside. And now I put the cap on here. Now what we're looking for is, as the gases are now, number one is they're evaporating, coming off the cotton wool, and the gases are now moving down the tube. Now what this is hopefully going to enable us to do is to be able to see how quickly the diffusion is happening. Because the ammonia molecules have an MR of 17. That means they're very light. The hydrochloric acid on this side has an MR of 36.5. These are much heavier. What that means is we are not going to see the gases meet in the middle and form the smoke here. The ammonia is going to be travelling an awful lot quicker. So we should hopefully see the white ring appear somewhere around here. It's not going to be really close to the HCl, but it should appear, give or take, around about here. Got it? So guys, we've been waiting about 2.5 minutes and we've formed a perfect line just there. So if he zooms right or gets in as close as he can, you can see the little cloud of smoke where it's met. It's formed a rather lovely, can you see that, Anand? The line. It's a beautiful line of smoke where it doesn't seem to be passing it. So the ammonia molecules, in that 3.5 minutes, have travelled this distance. Oh, I've got some lovely turbulence now happening within them. So you can clearly see that the smoke's forming and it's moving out. And it's actually, one of the lovely things here is we can see the diffusion process. Those particles, those gas particles, or in fact, we're forming a solid here, which is why it's a smoke. But the gas particles are moving at hundreds of miles, hundreds of meters per second. Gases travel very quickly. The reason why it still took 3.5 minutes to get down here is because the particles are moving randomly. They're colliding with the walls, and of course they're colliding with the air molecules themselves. So it slows down their progress. So the diffusion takes several minutes, even though it's traveling at very, very, very high speeds. So we can see the ammonia molecules, MR17, has traveled this distance. The HCl, which I even put in first, MR36.5, traveled only this distance. And that had a very similar, that had actually a slightly extra length of time. So nice to see our band forming off-center and about 1/4 of the way towards the HCl. Rather nice that. Okay, on to the next one. I'll put the lids on all my concentrated answers. Okay guys, so next one Now, this one's quite tricky. I have a fume cupboard on standby for this, because what I'm hopefully going to do, and this is, again, not an easy demonstration, I want to show you two gases in comparison. And both gases are brown, and of course that's on purpose, really. I'm choosing the gases so that students would immediately think that they are the same. But when we compare their rates of diffusion, we'll hopefully be able to tell which one's heavier. Remember that lighter molecules will diffuse more rapidly. So this liquid in here, I'm now adding is called bromine water. So I'm going to add a nice healthy amount of bromine water. Right, put the lid on there. Now what you can see with bromine is, number one, I'm now going to put the lid on, just like this, and leave a tiny air gap. So what's now happening, if Anand can get a bit closer, we have got bromine water down here. By the way, observation for year 11s is it's orange. Also for A level, test for alkenes, we've got orange and it's producing a brown gas. And that gas is bromine as Br2. Now what you notice is that it's completely colourless at the top, so the gas is actually sunk down, and we've got it being a pale brown here. Now that gas, bromine, is very heavy. Bromine's atoms weigh 80, have an atomic mass of 80, and it's in a pair, which means these molecules have an MR of 160. They are very heavy, so they tend to stay on there, but they will spread out over time. They will diffuse still. So if I do the next one, this is now the next gas. This is another brown gas. This one is nitrogen dioxide. Now NO2, we don't get NO2 in bottles. We have to manufacture it. And the way that we do this is we take another, by the way, another concentrated acid. So I'll return to my gloves. This time, I'm using concentrated nitric acid. This is formula HNO3. It's one of those forgotten acids, poor nitric. And nitric acid is it's a lovely acid because it loves to eat metals. It's incredibly corrosive when it comes to metals. So I pour in a small amount of concentrated nitric acid. Just a small amount. Don't need much of this. Just like that. So that's HNO3. You can see again it's fuming. Okay, and what I'm now going to do, just move that out of the way, and I'm just now going to add a tiny piece of copper. Don't need much. You can see how much I'm going to add. What I'm hoping to see here is, there you go, there's my copper. So copper metal, colour of GCSE is pink or brown, not orange and not copper. So I'm going to add this to it, and this is going to react with the nitric acid, and it's going to form brown NO2 gas. So you can see I've got another brown gas being produced down here. You can see that this one is already spreading out. It's up to about this point now. And you can see I've generated a very small amount of NO2, which is another pale brown gas. You've also got, at the bottom, I've formed a green solution. And this here is now copper nitrate. Now, it looks green, and it is green, in fact, but when you add water, it'll turn blue. But you can see that the brown gas is slowly moving up the jar. So it's actually getting paler. You saw how dark it was originally. I want to try and have a similar amount of gas. It's now up to here, and it's slowly moving up. Now, nitrogen dioxide has a formula of NO2, which means it has an MR of nitrogen being 14 and two oxygens, each being 16, 32 plus 14, 46. So this bromine with an MR of 160 versus 46 of this one. And you can see the brown gas is now up to about there, and it's spreading out. Now what they'll do at GCSE is they will compare these two brown gases, and they will show you the image of before, brown gas is here, and then they'll show you a time delay, they'll show you a picture of it later on, showing the fact that it had been standing for a few hours, and what you'll notice is this one's up to here, and this one's only up to here, showing that the gases are diffusing at different rates. Once again, if you did this, by the way, there's another demonstration that's often shown, which is to have another chamber on top, where you make this one a vacuum, and when you move it, it moves up. We know that the diffusion is slowed down by the other air molecules and the molecules moving randomly and colliding with the walls. So if you remove the air, then it will diffuse much more quickly. Brown gas is slowly working its way up. I'm tempted to actually make it a little bit more to make it darker, but it's quite nice that you're seeing it get paler down here and the gas is diffusing further. But again, all about the gases and their MRs. I just thought I'd do one more demonstration. That brings me to the end of what you need to see. Oh, before I do this, just come back over to my potassium permanganate. And what you can see is, if Nan gets down, we've now got a uniform concentration up here, but look how dark it is down here. So we have a dark purple at the bottom, and it's sitting down there. So it's dissolved, but the diffusion is incredibly slow. Unlike the gases, where it's diffusing relatively quickly, I would have to leave this for an entire night time for it to diffuse through the solution and form a uniform gradient in terms of the purple. Uniform gradient. A uniform colour all the way through. Maybe I'll do that. I might show you a picture of that tomorrow. I might come back to the video. Do you know what? I'll end that there, folks. Thanks for listening. See you soon.